SwayamPrabha. Digital India. Educated India.
Welcome to lecture 4 of the Statistical Thermodynamics for Engineers. So, in this particular class, we are going to first start doing what we call the combinatorial analysis for statistical thermodynamics. Okay, all right. So, in this particular thing, as we stated previously, that in quantum mechanics, ultimately what does quantum mechanics do? And this establishes the relevance that why we are studying this. That the quantum mechanics, we already said, that dictates that the energy levels are discrete. So, discrete energy levels, right? Okay, for molecular systems. So this we already did in our first class. Okay, we'll later on see that the energy level is not the only thing. It has something called energy states as well. But we will see that a little bit later, and that energy states are called degeneracy. But for the time being, let us take a pause, a little bit of a pause, and let us try to see that how we can establish some statistical techniques before we delve into what are the energy levels and what are the energy states. Okay, so we'll come to that in a little bit later. Okay, so first, before doing this, let us look at something called distinguishable. Let us establish a few concepts like distinguishable objects. Okay, so what do we mean by distinguishable objects? Okay, so distinguishable objects has got basically three significant cases attached to it. Okay, each of this can be considered by posing slightly different fundamental query. Okay, so let's take the first one. Okay, so the subject is distinguishable objects, in which you can distinguish the objects from one another. So let us ask the question that in how many ways in identical but distinguishable okay, objects okay, be placed okay, in m different containers okay, with a limit of one object per container. So you got the point. So the question that we fundamentally want to address over here is that in how many ways in identical but distinguishable objects can be placed in m different containers with a limit of one object per container. Okay, so the limitation of one object per container requires that your m should be less than equal to n, right? M is greater than n, then this particular thing cannot happen. So what happens here? The first object can be placed in any of the m containers, right? The second object can be placed in m-1 container. The third object can be placed in m-2 containers, right? In any of those two containers, right? So that if I write it properly, so the first object, okay, can be placed in any of the m containers, right? Similarly, the second object, we take the second object, okay, that can be placed in m-1 containers. correct? And so on and so forth. So the total number of ways becomes, if I write it as W1, what does it become? M into M minus 1 into M minus 2, so on and so forth, M minus N plus 1. That is the limit. Okay? In other words, W1 becomes M factorial divided by M minus N factorial. So this is the first query. I think we understood it very clearly that when there are this kind of objects and there are M containers, they can be arranged. The number of ways in which they can be placed is given by this. Okay. Now let's ask the second question, again with distinguishable objects. Here the question is, in how many ways may n identical, distinguishable, once again distinguishable objects be placed in m different containers, those parts are all the same containers, such that okay, ith container holds exactly in I objects. So you got the question, right? Previously we said there should be like n different m objects are placed in n different in m containers, such that there is a limit of one object per container. Here we are stating that n identical but distinguishable objects are placed in m different containers, such that the ith container contains ni number of objects, right? So we know for sure in this particular case, if we analyze the problem, the total number of permutations for n objects is n factorial, correct? But however, within each container, the permutations are irrelevant. Correct? As we are only concerned with their number rather than their identity. Since we are concerned about their numbers, and not identity. Right? So we are only concerned, we do not want to differentiate between Ram and Sham. We don't want to differentiate like that. We just are concerned about the number, right? So even though n objects can be permuted in n factorial ways, but within a particular container, their permutations doesn't really matter. So hence what happens is that this n factorial, so therefore overcounts, correct? It overcounts, okay? Overcounts the number of ways in which this arrangement can happen. Okay, so therefore we have to correct for it. So therefore the number of counts becomes, if I write it as W2, this becomes n factorial, then it becomes y equal to 1 to n in I factorial. Okay? Understood the point? So this then becomes, this overcounts. So now therefore to get the real answer, we have to divide by the individual permutations that happens within the containers. We have to take that out. Okay? So this is the ultimate result that you should get. Okay? So these are for n distinguishable objects arranged in m containers such that the ith container contains n number of objects. Okay? So therefore, this brings to the third question. Okay, so in the third question, once again, the question is the same: in how many ways n identical, distinguishable objects, okay, be placed in m different containers, with no limitation. Now the question is with no limitation on the number of objects, basically number of objects per container. Gotcha. Okay. So here, therefore, the answer is since there is no limit, okay, it becomes fairly easy. Your W3 becomes m raised to the power of n. Right? Okay. So this brings the third possibility. So for distinguishable objects, therefore, there can be like three types of questions that we ask, fundamental queries, and we will see how they are linked with the quantum mechanics, or the statistics of the quantum mechanics. And the answer is pretty clear that these are the three different ways, the number of ways in which the objects can be arranged in n different containers. So this brings us then to indistinguishable objects. Alright, so indistinguishable objects. Okay. So there are therefore now two cases of significance that we can ask, that same way that we ask the question with distinguishable objects. Here we ask the question for indistinguishable objects. Let's name it as 4. So in how many ways? The question is n, once again, identical. Now it is indistinguishable. Objects be placed in m containers with one object, basically one object per container. So this is a imposition that I have. Okay, excellent. So now for indistinguishable objects, okay, any rearrangement among the n objects cannot be recognized, right? So therefore, the W1 that we saw previously, that overcounts the number of ways in which indistinguishable objects can be arranged by a factor of basically n factorial, right? So if we look at the first case over here, okay, so that was the case, if you recall. This was the total number of arrangements that we had. Now, because the objects are indistinguishable now, okay, so any rearrangement among n objects, okay, yields nothing, right? That means it is not recognized, right? You cannot differentiate. As a result of that, your W1 overcounts, right? So, and overcounts by a factor of n factorial, essentially, right? So your W4 therefore is written as m factorial. It is almost similar, divided by n factorial. So this is the new one, and m minus n factorial, right? So as you can see, so this is the way, this is the same question as question 1, except that the objects are indistinguishable now. Now comes the fifth and more or less the final query that we would do over here. Once again, it is n identical. indistinguishable objects. The same question with no limitation. No limitation on the number of objects per container, and there are n containers actually, right? So it's the same question as case 3 over here. Now this is a fully unconstrained case. Now let's look at it a little bit carefully. These are indistinguishable objects. There is no limitation on the number. So it is almost like saying that let us actually initially assume that the distinguishable objects are labeled as 1, 2, 3, 4, 5, 6 all the way up to n. Now let us now arrange these objects in a row with m containers which are basically separated by partitions. So basically you are putting partitions, okay? And so that is an example that you can think of. So let's put it in writing. Say we begin by stating the obvious that we should initially assume that the distinguishable, let's assume these are indistinguishable objects, and they are labeled 1, 2, 3, up to n. Okay. Now let us arrange these n objects. If you look at it, arrange these n objects in a row with m containers identified as partition. Let's say this is a partition now, then 4, 5 is another partition, then 6 is another partition, then goes on, and then n minus 1 is one partition, n is one partition, something like this. So these partitions are basically the container partitions, right? That we have put. Okay, so these partitions, okay, basically identify the containers. Okay. So this is one example. I mean, this is just to put a perspective that how such a arrangement can be made. Okay, so you can see 1, 2, 3 are there in partition 1, first container, and then 4, 5 in second container. So this is first container, second container, third container, all the way up to whatever number of containers are there, like n container. So now, regardless of their actual arrangement, the maximum number of arrangements among n objects. So there are n objects, as you can see over here. Okay, and then there are n minus 1 partitions. So there are n objects and m minus 1 partitions. Am I right? There are n minus 1 partitions. Right? So the total number of objects, if we just put it that way, is this. And that by interchanging the partitions and all those things, you know, this maximum number of rearrangements that can be made is therefore m plus 1 factorial is the total number of ways, okay, in which rearrangements, or the maximum number, this is the maximum total number of ways in which rearrangements can be made. Arrangements can be made. Excellent. Okay. So, but however, interchanging the partitions produces no new arrangement, right? If you just change the partitions, it doesn't result in anything. So therefore, we have overcounted. By m minus 1 factorial. It's the first overcounting, right? And since n objects are actually indistinguishable, now on the top of that, n objects are also indistinguishable, right? Indistinguishable. So that means that we are again overcounting. By n factorial, right? So therefore, the total number of ways in which this arrangement can be made is n plus m minus 1 factorial divided by n factorial into m minus 1 factorial. So you understood the premise of this particular problem is this. First we assume, let us assume all the objects are distinguishable and we label them 1, 2, 3, 4, 5. And then we have the partitions also. Those are also like objects. So now we arrange them in whatever order, like this order that you see over here, right? So this is one arrangement. Now similarly, by changing the partitions and the objects together, we can get this number of maximal arrangements that are possible. But since these partitions can be interchanged, it does not produce any new arrangements. So therefore we have overcounted by m minus 1 because partitions are indistinguishable to begin with. Now the objects are also indistinguishable. So therefore, again, the rearrangement among the objects also does not. So everything is 1 or everything is 2. So there is no new arrangement that can be made just by changing the objects. So therefore we are again overcounting by n factorial. So therefore this becomes the total number of arrangements that are possible. Okay. So for this. So we have considered therefore 5 cases. Like cases 1 to 5, right? Which for of those cases 3 are for distinguishable objects and 2 are for indistinguishable objects, right? So these are the 5 cases that we have done. Out of these, cases 3 to 5 is what is of relevance. So cases 3 to 5 will be essential for what we are going to do next. Essential for what we are going to attempt. After we learn a little bit of the quantum mechanics. So 3 to 5 is the essential for what we... So 3 to 5 are what? 3 to 5, 3 was n identical distinguishable objects placed in n different containers with no limitation on the numbers per container. So any number can go in a container. That is case 3. Case 4 is n identical indistinguishable objects with a limit of 1 per container. And case number 5 was the same thing, n identical indistinguishable objects once again, where there are no limitations on the number per container. Okay, so let's just look at a simple problem. Okay, let's say a problem just to give an idea. So determine the number of ways of placing 2 balls in 3 numbered containers. Okay, 3 numbered containers, such that, let's take the first case A, where the balls are distinguishable and no limit on the number per container. Okay, so this is basically your case 3. So it is given as n raised to the power of n. In this case, there are 3 containers, 2 balls. Altogether, the result is 9. 3 raised to the power of 2 is 9. Okay. You can also put all these 9 cases and see for yourself what will happen. Now, if I take the second case where the balls are indistinguishable now, with a limit of 1 ball per container, right? Okay. So this becomes your case 4. And these balls are indistinguishable with limit of 1 ball per container. So this is now becomes your W4, which is, if you recall, is m factorial, n factorial, m minus n factorial. So it is basically 3 factorial divided by 2 factorial and 1 factorial. So this is 3. So you can see the number of ways have kind of reduced in this particular case, right? And then comes, if you can consider another point, which is C, which is basically the balls are once again indistinguishable. With no limit. This time there is no limit on the number per container. Right? So that becomes your W5 case. So W5 case then becomes, if you recall, n plus m minus 1 factorial divided by n factorial m minus 1 factorial, just to take into account the overcounting. So 4 factorial divided by 2 factorial and 2 factorial. This becomes 6. So the answer becomes 6. Okay. So this is just an example problem. Now case A, where the balls are distinguishable and then there is no limit on the number per container. This has got a formal name. This is called the Boltzmann distribution, as we will see later. Boltzmann distribution. When the balls are indistinguishable with a limit of 1 ball per container, this has got a name. It is called Fermi-Dirac statistics. That is the Boltzmann statistics. We should write statistics. So this is Fermi-Dirac statistics. And the last one, which is indistinguishable with no limit on the number per container, this is called the Bose-Einstein statistics. Bose-Einstein statistics. Okay. So Boltzmann statistics deals with objects which are distinguishable, which can be placed in M containers. Containers, we will see what containers actually means in terms of statistical thermodynamics. But assume that these are particles which are distinguishable and then there is no limit on the number per container. Then that is called the Boltzmann statistics. Okay, and that is your W3 over here. When the object, the particles becomes indistinguishable and with a limit of 1 per container, then that is called the Fermi-Dirac statistics. And your electrons and all other things follows the Fermi-Dirac statistics. And then when they are indistinguishable with no limit on the number of particles or balls per container, that is called the Bose-Einstein statistics. Okay. So this is S.N. Bose, and this is the famous Bose-Einstein statistics that we are talking about. So just by looking at some analysis and taking analysis from your everyday life, just by objects or balls or whatever you can think of, we can kind of draw a parallel to the corresponding elements in statistical thermodynamics. And exactly we are going to next cover that what are energy levels, what are energy states, and how these things can be manipulated, and what will be the different types of things that we will get when you read about energy states and energy levels, what is degeneracy and stuff like that. And then we are going to work out the Boltzmann statistics, also called Maxwell-Boltzmann statistics, and the Fermi-Dirac statistics and the Bose-Einstein statistics, and see that how, from a probabilistic point of view, from a permutation point of view, from a combinatorial point of view, how we can evolve some of these statistics that we can apply now to real particles, to real systems. So this is the end of your lecture 4. We will now meet you again in lecture 5.